Right. Good morning, everyone. Today I'll be presenting on development of a screening tool to predict optimum fly ash dosage for ASR mitigation in concrete structures. My name is Pravin Saraswatula. I'm the PhD candidate at Texas A&M University. My co-researchers are Dr. Anil Mukhopadhyay, Senior Research Scientist at TTI, and Kai Wai Liu, who is Assistant Research Scientist. So ASR remains one of the major durability issues affecting concrete structures, primarily infrastructure like bridge, legs, and pavements. So what are the three things required for ASR? We need high alkali, concentration of alkali hydroxides in pore solution, which is also pore solution alkalinity. We need reactive silicate minerals in the aggregates. In presence of moisture, it forms an ASR gel, which is extremely hygroscopic and expansive, which can lead to extensive cracking. So in summary, we need three requirements for damaging ASR. One is sufficient quantity of reactive silica from aggregates, a high pore solution alkalinity, primarily coming from Portland cement, and third is sufficient moisture. So for ASR mitigation, one of the primary approach is to design by avoidance. So it's talking about elimination of these requirements. The first one would be use of non-reactive aggregates, but it's not always feasible because sustainable practices require using locally available materials. So a second option, people also researched on the use of low alkali cement to lower pore solution alkalinity. Now, this is not really effective by itself because the ASR initiation depends upon the total alkali level in the concrete, and especially some of design practices use about 600 to 700 pounds of cementitious materials. So the third option, the use of SCMs, especially fly ashes, is actually the most common practice for ASR mitigation. When we look at what are the proposed mechanisms for ASR mitigation, some of them being the reduction in pore solution alkalinity or total and microstructure refinement, as well as tensile strength improvement. But we also know that some of these fly ashes contribute a tremendous amount of soluble alkali into pore solution, both at early stages as well as at the later stages. So this object pore solution modification is actually the governing aspect for ASR durability. Theoretically, a lot of thing is always focused on reduction of pore solution alkali, but incorporation of fly ashes also increases also contributes the additional soluble alkali into pore solution. So that is one primary aspect to remember. So when we look at the performance based evaluation approach for ASR mitigation, the primarily focus is on determining what is the optimum fly ash dosage for ASR mitigation. One of the standard approach is to do the ASR tests, either 1567, 1293, 380, and as well as T142. One of the primary limitations is most of these test methods are time consuming and they are cost and labor intensive. So they're not really ideal for rapid fly ash evaluation. And the other is these test methods often have alkali boosted test conditions or alkali leaching. So the effect of soluble alkali from fly ashes, also the overall concrete pore solution, is actually not visible, except for the ASTO TP142, which is the accelerated concrete cylinder test. But with the major constraint of the time limitation, we look at what are the rapid approaches or the prescriptive approaches on how we can predict some of what is the optimum fly ash dosage for ASR mitigation. So we have three current approaches. One is the specification 1778. It's only applicable for class F fly ashes. Then we have two models. One is chemical index model, which is a regression-based model from ASTM C1567. And next is extended chemical index model, which is based on 1293 or concrete prism test. One of the primary limitations is these regression-based models rely on expansion measurements. So the effect of pore solution alkali or also the fly ash soluble alkali is pretty much not detected. And what's overall what is the current challenge is there is a continuous change of fly ash composition. The traditional varieties of class F and class C fly ashes are continuously decreasing because of environmental regulations on these power plant operations. So that has led to newer alternative varieties of fly ashes, such as blended coal ashes, blended fly ashes, ponded ashes, as well as remediated ashes. So overall, there is a decreasing availability of conventional ashes, and there is increasing availability of like the unconventional ashes. So how can we apply pore solution for rapid ASR evaluation? If you look at overall pore solution chemistry of concrete mixes, we have total soluble alkali as opposed to bulk alkali, which is actually contributed by all the concrete ingredients into the pore solution. The second aspect is alkali binding by the which actually uptakes some of these alkalis from the pore solution and reduces their concentration. This total soluble alkali consists of two aspects. One, which is contributed at very early ages, and second, which is actually released as a function of degree of reaction. Now, similarly for the alkali binding, this also depends upon amount of hydration product and the stoichiometric composition of hydration product. So it's a function of degree of reaction. So overall, like if we see different behavior of fly ashes with respect to cement, we have a tremendous contribution of class F ashes, followed by class C ashes, followed by class F ashes. Whereas for the alkali binding capacity, it's F followed by class C. So what we have noticed from our research is the most critical aspects for a rapid ASR evaluation can focus on following things. One is early age alkali contribution from fly ashes, because it probably leads to a high pore solution alkalinity, which is critical for ASR initiation in many of these cases. Second, the alkali binding, which also depends upon the amount of hydration product, offsets some of the bound alkali. So just focusing on the readily soluble alkali can give us one of the rapid approach. And third, since the total soluble alkali for fly ashes, which was earlier measured by ASTM C311, is not in practice anymore. So a performance-based test that can readily measure this particular aspect can be used, is best suited towards an overall performance-based evaluation approach towards ASR evaluation. With this, like our overall goal is to develop a screening tool that predicts optimum fly ash dosage in concrete for ASR mitigation. So what we do for that? First, we investigated water-soluble alkalis or the early age alkali contribution from fly ashes into pore solution. Next, currently, like this test method, ASTM C114, has not been standardized for fly ashes. So we use some data points from literature as well as our experimental studies to develop a non-linear regression model for prediction. Third, developed the TTI model 1, which focuses on estimating the overall pore solution alkalinity, taking into the combined effect of soluble alkali from cement as well as water-soluble alkali from fly ashes. And for this, empirical equations from Snyder et al. Were used. Finally, all of these things are combined towards a screening tool development, which actually predicts the optimum fly ash dosage for ASR mitigation, the PSA coming from TTI model 1, the aggregate threshold alkalinity, which is coming from this research study. And finally, a validation study was performed to evaluate the effectiveness of the screening tool in fly ash dosage predictions. Briefly going over the overall methodology, once we have total water-soluble alkali from fly ashes, which can actually be experimentally measured. But if the experimental method is not possible, then we also developed a non-linear regression model to predict this. And finally, the TTI model 1 estimates the overall pore solution of alkalinity of concrete based on cement and fly ash composition. And the aggregate threshold alkalinity can actually be measured, or there is a direct relationship which gives a conversion from THA to reactivity. Once both THA and PSA parameters are known, the overall screening tool optimizes this to determine what is the percentage fly ash needed for ASR mitigation. What are the major findings of our study? One is, addition of fly ashes is always expected to lower the pore solution alkalinity of concrete mixes. But some of these fly ashes, especially class F and class C, actually contribute to very high levels of soluble alkali. As you can see, this is the PSA of just 100% cement mix. And when we look at like 25%, 35% class C and blended ashes, it's almost like some of the data points are really close to the original 100% cement mix. So there is a significant modification of concrete PSA by fly ashes. The overall non-linear regression model that we developed in this study with 61 data points, it showed a good reliability in the WSA prediction from these fly ashes. The TTI model 1 that we developed, it combines the soluble alkali from cement and fly ashes has shown a good reliability in PSA determination. We compared it with the experimental studies as well as thermodynamic modeling, and we noticed a MAE of 4.3%. This is the most important aspect, like for screening rule predictions. One is, as the percentage replacement of fly ash increases, the concrete pore solution alkalinity would actually decrease. And the threshold alkalinity to aggregate reactivity conversion can be from the previous research study. So for this particular research, the lab test was conducted for R2 aggregate with the threshold alkalinity of 0.34. And the screening tool predictions for this R2 aggregate for these two fly ashes were 48 and 28%, whereas with the actual ASR test, we noticed it to be around 45% and 25% for these two respective ashes. So basically a comparison of concrete PSA and aggregate THA. And it's important to notice that this is not a regression model. This is actually focusing on two fundamental aspects, which is pore solution alkalinity and aggregate threshold alkalinity comparison. So in this overall study, we evaluated 27 fly ashes, which is a combination of class C, class F, blended fly ashes, as well as some reclaimed and natural pozzolans. So about like 80% of the fly screening tool predictions actually matched with the ACCT test. Of this, 33% were the cases where 1567 actually underestimated. Now, we actually discussed in the previous slide that this test, although it's rapid, but there's a significant alkali leaching that actually affects the ASR measurements. So the screening tool is pretty good, reliable in terms of predicting the fly ash dosage even in those cases, and which is well supported by the ACCT test. And around 15% of the data points, which is 4 of 27, there was a deviation more than 5 to 8% from the two ASR tests. One of the important aspects also from this study was more and more we have blended ashes which are coming up. And some of these ashes, like when we classify by the traditional, like F8, when we use ASTM C618, it actually is shown as class C, but when we consider the mineralogy, it behaves as class F. Now this ASR test, the blue one, is able to detect that effect. And we know, we realize that the overall replacement level of 30% is able to mitigate ASR. But some of these empirical models like chemical index and the extended chemical index is not able to detect those effects because they traditionally rely on the bulk oxide composition. So as is, like they just go by ASTM C618 classification, which is not reliable. So how does the development of the screening tool overall help in the ASR evaluation? One is significantly cuts down the time as well as the effort needed for the ASR test, so that we can actually select only very specific ashes and only one particular replacement levels, which can benefit both cost as well as labor savings. So with this, like currently this test can be performed in 1 to 2 hours, but since it's not standardized, the water-soluble alkali can be instantly predicted using the nonlinear regression model. So the second step would be compare whatever fly ash dosage we are getting with the 1567, because this is the current standard practice that TxDOT uses for determining what is the optimum fly ash replacement for in these cases. So wherever there is a deviation of more than 5 to 8%, then selective ACCT validation is required only in these cases. So in terms of like overall this thing, if we have 10 fly ashes, what we notice in the lab is that the number of fly ashes that need the long-term ASR study would actually come down to maybe 3 or 4. And going over like just a general overview of how the ASR, the screening tool is performing with respect to different prediction models as well as the ASR test. So consistently, like we have been noticing, irrespective of the ASR test, it has delivered a lowest MAE, both with the ASR test as well as prediction models. But this is the most notable feature, that it is able to cater the unconventional ashes as well as the reclaimed ashes pretty well. So overall, in conclusions, the consideration of concrete pore solution alkalinity is very important for ASR evaluations. Now, traditionally, fly ashes are incorporated in concrete, and it is assumed that it lowers the pore solution alkalinity, but some of these fly ashes significantly modify because of high soluble alkali contribution, and accounting for that is pretty important. The TTI model 1 that was developed in this study has shown a good reliability in PSA determination. It's very important to note that this is not a regression model, but optimum fly ash dosage is dependent on two chemical parameters, which is concrete PSA and aggregate THA relationship. And this research has also verified that this relationship actually holds well. And finally, the screening tool predictions has demonstrated a low MAE for ASR tests, and more importantly, catering to unconventional ashes, blended and reclaimed fly ash varieties. This research has been selected for the TRR publication, and another paper is in works for the ACI currently. But I would like to acknowledge the Texas Department of Transportation, American Coast Ash Association, which actually gave a fellowship for this research, and Bureau of Reclamation Studies, as well as Los Alamos Laboratory